Okay, welcome to the session titled All Audio in an All IP Production Facility. Andy Rayner is going to be getting up to give what always proves to be a very engaging discussion. So look forward to it and take it away, Andy.
Thank you very much, Wes. Good morning. Good morning. I stumble onto the stage. Just trying to see if we can get this working. So a little bit of background. The immediate background is that this morning I did the 4K race. So if I fall asleep or don't keep my legs up halfway through, then that's why. One of my colleagues is sitting over there. He was actually, I think, 8th in the race out of 500. I think I was probably more like 350 or something. But I did it in 24 and a half minutes, I think. So that was this morning. I took this picture 2 years ago of someone at the race because I thought that says it all. I must have been pretty near the back. I worked for BT for 22 years, and then I was persuaded to jump to the dark side, to Vendorland. And this was the modified BBC test card that I was given as a commemoration when I left BT. I've never had hair anywhere near that long, even when I had some hair. Okay, so that's a little bit about me. Moving on to the topic, audio. Now, audio is quite often the poor brother, or perceived as the poor brother of the video. We've spent a lot of time, even in things like the 2110 suite, focusing a lot on the video and not the audio. But actually, two things. First of all, the complexity of an audio setup in any environment, live event or a production environment, is generally far more complex than the vision. And secondly, just in terms of the IP story, the IP journey of media over IP, the audio guys got there way ahead of the video guys in terms of uncompressed audio. Are we good there? Are we good there? Okay, so the audio, is this right? Move it up a bit. Okay, so the audio guys got there first. Now, audio has lots of challenges. None the least is that because have we still got some problems? Have we still got some problems? Is that better? Bob's waving to me from the back. Yeah, okay, that's good. So some of the challenges are there's lots of audio formats around. So we've done, we've lived through analog AES, SDI embedded audio, and then 22-6 embedded audio. A lot of us embraced the EBU 3326 recommendation for audio, and then came AES 67, and then lots of people are using MADI. In fact, MADI has had a kind of resurgence in the last few years, given its longevity. And then people also using things like audio over Ethernet, which aren't strictly anything to do with IP, but use some similar transport technology. So focusing now on the three key formats there, and very specifically for the interest here, the 2110-30, which to all intents and purposes is a subset of AES 67 in how it does audio. And whilst we're on this slide, it's just worth saying that a lot of these audio formats, in terms of the data plane, have a lot of commonality. The challenge is the control plane, and we're going to talk about the maturity of the control planes for audio as we move through this presentation. So the suite of SMPTE 2110 standards has evolved significantly over the last couple of years. I think this time last year we had -10, 20, 30, and -21 defined, which were the basics of the uncompressed video and the uncompressed audio, and then the related system level and timing information. We've since added to those. We've added the ancillary data. We've added compressed video essences. We've actually added uncompressed audio, and very specifically the difference between -30 and -31 is -31 carries transparently all 32 bits of your traditional AES frame, rather than the -30, which carries 24-bit PCM. And very specifically, the aim of this is to use it for non-PCM applications. My microphone's slipping all the time. So this is designed, -30 is designed for PCM audio. Anything that's compressed or non-audio should be carried as -31. And then we've added lots of things, including some stuff that's even in conception at the moment, the fast metadata -41 and 42. And this, for completeness, dash 23 is for high frame rate, slow-mo type applications for video. So where we've got to, as I say, a lot of the audio systems, which I call proprietary systems that have been in existence, IP systems for the last few years, have had relatively straightforward data forwarding planes, but the control plane has been the thing that's been a challenge. And if we look about the maturity of the 2110 take-up in the industry over the last couple of years, one of the biggest challenges I think the industry has had, being honest, has been the maturity of the control plane. We've actually been able to interface the data quite effectively, improve that, but really only recently, and I think, speaking from our company perspective, I think we've only actually this year at the beginning of 2019 done our first full true NMOS deployment. Not that we haven't been ready before then, but the whole marketplace is only maturing with that NMOS capability on enough products to make it come together this year. So a lot of people are now doing specifically ISO 4 and ISO 5, which are respectively registering and discovering devices, controlling them, and then also very important as an extension for audio is ISO 8, which is the ability to route and direct sub-channels within a multi-channel audio bouquet that's being carried. And very specifically, what happens at the control layer is we have devices registering themselves and then the control layer talking to the end device and telling it where to go. It's also worth saying that the way audio has been traditionally handled in IP, both in terms of being routed through the network and in terms of the way it's being subscribed to, is a tad different to the video. And that's possibly been because audio is so small, comparatively speaking. Audio is, at best 1,000th of the data rate of the video. So you can actually afford, in most audio environments, to actually pretty well broadcast the audio and have it available, all of the audio elements available wherever you need. Specifically with video, that's impossible to do, and you need to specifically route the video. Trying to move on here. So here's a few things. I want to share a few points. I hate slides with bullet points on, so I'm going to talk through this briefly and then get to a few more pictures to talk about some other things. So first of all, I think one of the lessons we've learned in terms of the customer requirements that we've had in studio deployments in recent times has been keep it all IP, don't go back to baseband. Now this has to be the approach that we have. If we're going to leverage the benefit of IP in terms of the flexibility of the reuse of rooms and facilities and equipment and people, then actually keeping everything in the IP domain is very, very important. And audio, that's important, and we'll come back to one or two reasons why maybe some architectures haven't, or even still are not keeping everything all in the IP domain. One of them obviously is things like gain and delay capability are actually needed within the audio flow and within the audio workflow. So we need to actually keep those capabilities in there as well. Also, again, this is pretty standard for most people, but within a plant, typically everything's staying synchronized. So we have our house reference, we have our grandmasters, and everything, both video and audio, should behave in an ecosystem where everything is well timed. However, obviously, when we've got unknown stuff coming in, into our what we traditionally would have called our lines room in a broadcast plant, then we have to reconcile the video and we have to reconcile the audio. And if we're staying in the digital format with audio, then obviously sample rate conversion is the way to go. Obviously, if we've got compressed audio in a -31 environment, such as Dolby or something, then we need to be even more careful because we can't SRC it. So we need to do appropriate frame dropping, or multi-frame aligned dropping to actually keep things together. Another thing that's actually become very apparent and important is the actual flexibility to support different channel widths within 2110-30 channels or AS67 channels. And that's because, for a lot of production environments, we're seeing kind of what I call pseudo-MADI flows coming in, where people actually want to trunk a whole number of audios from a location for production work. So typically, if we go to the 125 microsecond packet period in AS67, we can do 64 channels of audio on one flow, and that's actually incredibly useful. Not only because it's easy to actually just only route one flow, but it's actually allows us to actually cope with the scale there. But also, lots of other things tend to actually need groupings. Some devices work with only 8 channels within an AS67 or a dash 30. Others only cope with stereos, and also what we're seeing is some devices needing to actually accept effectively the content from more than one AES30 signal. So there may be a commentary that's a mono that's coming in, there may be then some stereo that's coming from somewhere else, and a couple of other feeds from elsewhere. And those actually need to be, if you like, all entering a device. So what we're seeing is quite a lot of the need for the ability to shuffle and aggregate in the dash 30 world to actually concatenate audio channels into a single new AES-30 stream. Full mono shuffling. So this is interesting. For those audio purists, and I have to admit, sometimes I put myself in that camp. I am at heart an audio guy. Will tend to think of the if we've got phase coherent audio, i.e. a stereo image signal, or we've got a 5.1 signal, then there's something that really wrenches in my gut about breaking that up and routing it as individual monos. Now the theory and the practice of AES67/-30 means that actually everything about the RTP timestamping means we get sample perfect alignment. So there is no reason on earth why we can't do that. And indeed, some deployments that we've been involved in, this has been the kind of the modus operandi that people have wanted to use. They actually want to shuffle in the IP domain. So the idea has been, if we break everything into individual monos, then we can actually do whatever routing we want and then recombine. Having said that, I think most of the deployments that we see, typically people are actually retaining at least phase coherent images together. So like the stereos and the 5.1s, etc. Full orchestration. So this is an interesting one, and there's I guess from a traditional audio perspective, because of the low bandwidth, people haven't needed to route audio. People have allowed it to exist in a multicast environment. That works well in a small campus, in a small isolated production island. But when you're actually going further with audio, you actually then need to start actually considering routing the audio. So quite a lot of the solutions that we've been deploying, we have been explicitly routing audio flows within the fabrics, as well as explicitly routing the video flows, even though from a bandwidth perspective that may not be necessary. NMOS compliance is obviously important, and I think we're still in the ramp up to maturity on that, but we're actually getting there. And then kind of going back to my top point there, all IP processing. Let's try and make sure we evolve architectures where we keep everything in the IP domain. And I've just seen Andreas at the back, so a big plug. If you want to hear the real expert on audio, come back at midday, or stay at the end for Andreas's next talk. So how is NMOS working? So the concept is that all of the devices register themselves to an NMOS registry. And what happens then is, when you actually want to set up a connection, you actually, using ISO 5 and now ISO 8, we configure the end devices as to what they need to listen to. And if we're orchestrating and routing audio flows, then we actually will be also orchestrating the connectivity and the flows of those going through the system. So these here are typically the receivers in red here. So these are the things that are being talked to by the 05 and 08 to actually make the configuration for the receivers. And then introducing the switch fabrics here, we have this system where we've got the flows coming into the switch fabrics being received. And I say we typically are involved in controlling the routing of both the video and audio flows as they go through the system. So treating them very much as equal entities. So there's kind of two different bits of audio processing function that we've seen have been necessary within this. The first one has been what I call video-related audio. So within the plant, the kind of requirements we've been seeing is, native baseband SDI signals that have got, typically up to 16 embedded audio channels coming in. They need to be part of the mix and actually routed and processed. We're also seeing quite a lot of 2022-6, which is kind of basically SDI with the IP wrapper on. So we still need to do that kind of traditional SDI de-embedding function, albeit in the IP domain. And then we're obviously seeing -30s or AS67 flows coming in as well. So those are kind of all of the, what I call the video associated audio flows. And then we're actually seeing quite a lot of requirements for audio only manipulation. So I say MADI has had a resurgence. We've been interested to see how much MADI stuff has been actually deployed and being looked for in the last couple of years, given it seemed to have a bit of a lull in the early noughties in terms of its use. But also, obviously, we have AS67 feeds. We have typically an asynchronous, both asynchronous MADIs and asynchronous AS67s incoming or -30s incoming. So we have to do sample rate conversion, again, subject to it being PCM audio rather than compressed. And then, obviously, mopping up the traditional stuff, we have the native baseband AES3 digital and analog audios as well. So those are, if you like, two sets of audio stuff that we've needed to manipulate. So this is just kind of showing the ecosystem together here. So this is kind of our IP switch fabric in the middle of our production center. And we've got a couple of different scenarios. So typically, obviously, we aggregate lots of audio from a live event coming in. We've got a lot of devices which are interconnected in terms of mixers and processors and listening devices in there. Also, to add to the challenge, and typically this is where we kind of end up having to compensate for lots of latencies, things like remote commentaries, because typically these guys are working on a proxy video, which has been at least mezzanine compressed or heavily compressed before it goes out, and then they're re-entering the audio back into the chain, and that needs to be reconciled into system timing. So most of what I've talked about so far has been like in-campus audio. So what happens with the audio within the campus? But obviously, what we're starting to see, leveraging the benefit of IP, is actually federated production, where actually we're doing stuff in multiple campuses. Now that may be multiple facilities owned by the same entity. It may be, event stuff, or it may be actually even different organizations sharing production. And there's a few things that happen there. First of all, the latencies are a lot longer. They're not necessarily long, but they're a lot longer than we're used to within a campus environment, where they're almost negligible in terms of that. In addition, if the related video is being subject to compression, then we're actually having to do a lot more compensating of latencies of the audio as it traverses things as well. Also, in terms of the way audio systems work, certainly at the control layer and the control plane for audio, a lot of systems are limited to kind of layer 2, which works very, very well in a campus environment. But once we actually start going to multi-campuses, then we actually need more flexibility there. So just one or two things about kind of system timing. This is kind of relevant to the video and the audio, but I think it's just worth raising it here. Traditionally, in terms of the mindset that we've had, I think, both in AES67 and in where we've got to so far with the 2110 suite for all of the video, all of the media essences, is a link-based approach, where we've actually concentrated on defining how we actually reconcile the timing from this point to this point, but not necessarily reconciling the timing all the way through. So this is kind of how we work with timing. So, and this is possibly where some of the challenges have come in, both in the use of AES67 and the 2110 videos as well, is the transport layer RTP timestamp has become, at the point of origination, defining the point of acquisition of that video frame or that audio sample. And in the audio world, this RTP timestamp ticks at the sample rate. So in a nominally 48 kilohertz world, this is ticking at 48 kilohertz, which means obviously we have that unique timestamp for every audio sample. But the challenge we have is when we get into a concatenated production environment, because one of the beauties of an all IP environment should mean that we've got this origination time of our event, of either our studio cameras or event cameras and microphones, and theoretically, whatever we're doing in terms of audio mixing and processing here, whatever we're doing in terms of any video mixing, augmented reality, whatever stuff's happening in these workflows, when we get over to here at our use time, we really should be able to reconcile these timing flows automatically. There's no reason on earth why, we shouldn't actually be able to have enough information carried through the chains to actually allow us to reconcile that. Then that at the moment, to be candid, is a bit of a pipe dream, because most of these systems are actually, we're kind of losing the end-to-end timing, because everything, both in the AS67 world and in the way we do it in 2110 in general, is all about link timing and delivering from point A to point B, and we don't actually have an automated system of, if you like, aggregating the time taken for the different media flows. That's something we're actually looking to address in modifications to 2110 in the revisions at the moment, to try and get that at least as an option in the system. And I'll just talk you through that in a little bit. I think part of the reason why that's happened, and this applies again to both the video and the audio things, is typically, I think, a lot of infrastructure has been developed by, we've got our digital audio or digital video manipulation, and we've got an IP receiver that's been bolted on the front end and an IP transmitter at the back end, and it's not necessarily been obvious or easy for people to actually make the leap to be able to actually carry through timing information here, out there. And in fact, you may even hear a different view on this from Andreas in a minute. I'm not too sure if he's going to talk about this. But the important thing that we see in terms of preserving that timing through the chain, there's two questions. Do we actually do it using the RTP timestamp? So do we actually make sure the outbound RTP timestamp honors the relative timing of the inbound one, so we actually can do that math at the end? Or do we have some other information we carry to allow that timing compensation to be done automatically? So AS67 was ahead of the game, but when they did it, like I said, the audio guys got there way before the video guys anyway, and at least this link time, which has been deprecated as we went into 2110, exists in AS67 and doesn't in 2110, but we do need more than this to actually get that end-to-end timing flow. Another quick anecdote here is on Ptp holdover. So, back in the day, it was quite difficult to hold accurate time for a long time. But actually, with digital synthesis now and high precision oscillators, there is no reason why, if you actually lose your timing reference, not that that should ever happen, but it does, if you lose your timing reference temporarily, why you cannot carry on. A lot of devices, typically in infrastructure that I've seen, are very good at muting as soon as they lose muting, either visually or audially, depending on what kind of device, as soon as they lose their timing reference. There's no reason on earth why you shouldn't be able to hold over for the order of minutes in terms of being able to run this, and then gracefully migrate to the timing reference as it picks up. So one of the things I keep whipping our developers on is making sure that we have gracefulness with timing. I think I'm gonna whistle through this in a minute. Sorry, my microphone keeps falling off. This is just some stuff that I've been talking about previously, at what happens at the edge of the facility. And some of this is not particularly relevant to audio compared with video, but several things are. Specifically, that as we go off campus, we may have different addressing schemes. We may or may not be going into a 2022-6, so we may be embedding the audio again. And if we do embed the audio again, obviously at that point it's incredibly important that we've reconciled the timing, because while those essence flows are separate, it's reasonable for them to exist in a temporal time offset. But as soon as we go back to any composite, like an SDI type embedded world, then obviously those timing offsets need to be reconciled. It's also worth saying that the industry has really picked up on what I call spatial resilience. So this is what we call 2022-7. It's an RTP level packet merge technology. This has been in existence, and we've been using it for uncompressed -6 video for probably 7 years now, 6 or 7 years. But many audio devices have embraced this as well now, and in fact the qualification, the badging that you can see over there, a lot of that was actually testing this on all of the audio flows as well as the video flows and the ancillary flows. These other types of protection typically are more useful in the wide area networking than in the campus, but this has taken on almost universal use within the campus for all media flows. I've been heading up an activity group looking at how we actually trunk or aggregate and carry multiple essences, video and audio and ancillary stuff, over wide area networking for long distance. I'm doing a presentation on that, so if you're sticking it to the bitter end and you're still here late Thursday morning, do come along. I'm going to be giving an update on that technology, but you can also grab the presentation if you haven't made it by there. We've just got to the point of agreeing our first draft of principles there, so do come along and see that. This is some of the stuff that we've been talking about, how we protect flows. Some of that's kind of obvious. One of the things we've been specifically looking at trunking for is that each of these audios on its own, actually the packet period is actually quite long compared with video. If we're trying to do in wide area networking, as we sometimes, things like FEC, then actually if you apply it to individual audio flows, it can take a long time, because if you're producing a packet matrix for audio correction, that can actually take a long time. If we've pre-aggregated this with a 1 gig or even a 10 gig UHD video flow, then if we FEC this aggregated trunk, then that timing period goes to a minuscule level, and we're also subjecting all of the essences to the same latency. So my conclusions as we draw to a close here: audio is incredibly important. It is typically the most complex part of the system. The full compliance to the standards is important, and flexibility. And I think this is probably the most important thing here. That control layer for an open standards world is actually, with NMOS, is now maturing. And from our perspective, 2019 has been the year where we've actually seen true NMOS control for devices and solutions actually being fully deployed. So thank you very much for listening. And I'm in South Upper 5510. And I'd just like to say we do the best cups of tea at NAB. So if you want to come and chat through any of this or indeed anything else, do come and see me. I'd love to have a conversation, and I'll make you a very nice cup of tea. Thank you for your attention. Okay, thank you.
All right, thank you.